This is Multivariable Calculus, section 11.2, part 2, examples from your text. Here's number 6. I'm going to kind of mix up the notation. We have IJK notation, we have chevron notation, we have letters with arrows over them versus bold letters, both describing vectors. So 2a plus b, you double the components of a, which makes it 2, negative 4, 6, and add to that the components of b, 1, 3, negative 2, to get the answer. 3a minus 4b, you triple the components of a, quadruple the components of b, and then subtract carefully. A dot b, you multiply the components together and then add those products. The length of vector a minus vector b, first you subtract the components and then you square those results under the radical using the extended Pythagorean theorem. And then simplify the square root of 50 to 5 root 2. And finally, vector a divided by the length of a. Well, we already did we do the length of a? No, we didn't, did we? So you take vector a and you divide by the square root of the components squared, and that comes out to 1/14th. And then if you like, you can rewrite it in the IJK notation or just leave it alone. Example number 12. Find the angle between these two vectors in problem number 6. So we use our formula. We already did the dot product. We did the length of a. And there's the length of b using the components of b. Simplify and then use your calculator to do the inverse cosine of negative 11/14. Number 24. Write the equation for the sphere with center 3, negative 4, 3 that is tangent to the xz plane. Well, you know I love to draw a picture. So there's the center at 3, negative 4, 3. And if we draw a box to the xz plane, which is the plane coming out towards you, then the distance from that center to the xz plane will be the radius. So the radius is 4, and we have the center, so we just fill in our equation. X minus 3 squared plus y minus negative 4 squared plus z minus 3 squared equals the radius squared. Number 28. Find the center and radius of the sphere whose equation is 2x squared plus 2y squared plus 2z squared equals 7x plus 9y plus 11z. Well, we would need to put it in the other form. So the first thing I did was divide by 2. And the second thing I did was complain about those silly numbers. Why couldn't they have made it come out nicely? Grr. Then I brought everything to the left side. And then, yes, you guessed it, we have to complete the square 3 times. So we take half of 3.5 and square it, half of 4.5 and square it, and half of 5.5 and square it, and then add the sum of those 3 things squared to the other side, which I thought might be a nice square, but it's not. Then we factor, and so pretty obviously then our center is 1.75, 2.25, and 2.75, and our radius is the square root of the quantity on the right, which is approximately 3.961. Number 30, describe the graph of x equals 0. Well, what does this mean? This means x is always 0, but y and z can be any value. So in 3 dimensions, that is not a line. Y can be anything, and z can be anything. So any point on the yz plane is part of this graph. And so basically we just get the whole plane. The graph of x equals 0 is the yz plane in 3 dimensions. 38. Describe the graph of x squared plus y squared equals 0. Well, basically what they're doing is they're telling us that x and y are always 0, but since z is not mentioned, that means z can be anything. So this time we have to stay at 0, 0 on the xy plane, but z can be anything. And so x squared plus y squared equals 0 is the equation for the z-axis. Number 42. Given vector A is 12i minus 20j plus 17k, and vector b is negative 9i plus 15j plus 24k. Determine if a and b are parallel, perpendicular, or neither. Well, if a and b are parallel, then a would be a scalar multiple of b. And pretty obviously that's not working. So they're not parallel. If a and b are perpendicular, then the dot product is going to be 0. And the dot product is 12 times negative 9 plus negative 20 times 15 plus 17 times 24. And guess what? That is 0. Bingo. Therefore, a and b are perpendicular. 44. Determine if the points P, Q, and R lie on the same line. Well, there's Q. I did that one first because it was easiest. 3, 3, 3. And then there's P. And there's R. Now, I realize I didn't draw these super duper to scale, so it looks like they might be on the same line. Well, if they're on the same line, then these two vectors, QP, the vector from Q to P, and the vector from P to R, if in fact those 3 points are on the same line, then those two vectors should be parallel, should be in the same direction. So let's compute QP using head minus tail, and then let's compute PR using head minus tail, using those 2 points. And sure enough, pretty obviously, PR is twice QP, and therefore these vectors are parallel, and the points P, Q, and R do lie on the same line. Number 48. Compute the angles in a triangle whose vertices are given as follows, A, B, and C. Well, you know I like a picture. So there's my picture. And what we're going to do is we're going to get vector AB by subtracting B minus A. And then we're going to figure out vector AC by subtracting C minus A. And then what we're going to do is we're going to use our handy-dandy formula. Dot those two vectors together and divide by their lengths, take the inverse cosine, and turns out angle A is 90 degrees. Okay, so then we're going to do the same thing for another of the 3 angles. I chose to figure out angle B. BA by subtracting A minus B, and vector BC by subtracting C minus B. And then to figure out the angle B, we take the inverse cosine of that dot product divided by the 2 lengths, which comes out to about 68 degrees. And now that we've got 2 angles, all we have to do is subtract those angles from 180 to get angle C. Problem number 50, compute the direction angles for PQ given P and Q as these points. Didn't bother with the picture this time. To get PQ, we just subtract Q minus P. And then here are our formulas. And so for alpha, we take the cosine inverse of the dot product of V with I. When we dot V with I, we only get the first component, the I component of V, divided by the length. So angle alpha is 98 degrees. Same thing for alpha for angle beta, except this time when we dot beta with J, we get the second component of V, namely 3. And finally, gamma is the cosine inverse of the third component when we dot with K, divided by the length of V. And so those are the 3 directional angles. Problem number 54. Compute the work given if the force is this vector and the movement is in a straight line from P to Q. Okay, first we have to get the distance vector by taking Q minus P, because we're moving from P to Q. And then for the work, we just dot the force vector with that distance vector, and we get 48. Now it's your turn to work some problems. Have fun.